Hi everyone, today we're diving into a fascinating phenomenon called the Hall effect. It's one of those things that seems a bit mysterious at first, but when you break it down, it ties together a lot of what you already know about magnetic fields and electric currents. The Hall effect was first observed in 1879 by Edwin Hall. If you have a current flowing through a conductor and then apply a magnetic field perpendicular to this current, something interesting happens. An electric field appears perpendicular to both the current and the magnetic field. This perpendicular field creates a voltage across the material. This is what we call the Hall voltage. Imagine we've got a thin rectangular slab of a conductor, could be a metal or often a semiconductor. We'll send an electric current through it along its length, say from left to right. So we've got moving charges, typically electrons, going from one side to the other. Now we introduce a magnetic field, but here's the trick. This magnetic field is perpendicular to the direction of the current. So now we have the current flowing along the x-axis, the magnetic field applied along the y-axis. Here's where the Lorentz force, which you already know, comes into play. Remember that the Lorentz force is given by Q velocity cross product magnetic field. When the electrons move through the conductor, the magnetic field causes them to experience this Lorentz force. Since the magnetic field is pointing along the y-axis and the electrons are moving along the x-axis, the force from the magnetic field pushes them towards one side of the slab. This buildup of electrons on one side causes a negative charge to accumulate there, while the opposite side of the slab becomes positively charged. This separation of charge creates an electric field within the conductor, pointing from the positively charged side to the negatively charged side. That's the Hall electric field. As more electrons pile up on one side of the conductor, an electric field begins to develop, which opposes further electron movement caused by the magnetic field. Eventually, the forces from this electric field balances out the Lorentz force. At this point, the charges stop accumulating and the system reaches equilibrium. The result? We have a steady electric field across the width of the conductor, perpendicular to both the magnetic field and the current. This electric field leads to a voltage difference across the conductor, which we can measure as the Hall voltage. The Hall voltage, V sub h, can be calculated if we know a few details about the system. The current in terms of the drift velocity, Vd, can be written as I is equal to nqa V sub d, where n is the number density of charged carriers, the number of carriers per unit volume. Q is the charge of each carrier. A is the cross-sectional area of the conductor, and Vd is the drift velocity. Since A is equal to Wd, where W is the width of the conductor and D is its thickness, we get that nq Wd V sub d. Solving for V sub d, we get. Now we substitute in the expression Hall's voltage and simplify to Ib over nqW, where I is the current flowing through the conductor, B is the magnetic field strength, N is the charge carrier density, the number of charged carriers per unit volume, Q is the charge of each carrier. For electrons, this would be the electron charge, and W is the thickness, width of the conductor, in the direction of the magnetic force. This Hall voltage can give us a lot of valuable information, such as the type of charge carrier, if it's positive or negative, the density of charge carriers, and even the nature of the material, like whether it's a metal or a semiconductor. Now that we understand the basics, let's talk about applications now. The Hall effect is extremely useful in many real-world devices and industries. For example, Hall sensors can measure magnetic field strength directly. The Hall voltage changes with the strength of the magnetic field, so they're used in anything from MRI machines to mobile phones to detect and measure fields. In cars, the Hall effect sensors are used to measure wheel speed, engine RPM, revolutions per minute, and even the position of pedals. This helps in applications like anti-block brake systems, so ABS, and electronic throttle control. In physics labs, the Hall effect can help identify unknown materials by determining whether the dominant charge carriers are positive, like in some conductors, or negative, like in metals. Semiconductors are materials that have electrical conductivity between that of a conductor, like metals, and an insulator, like glass. This intermediate level of conductivity is what makes semiconductors so useful in electronics. Unlike conductors, where electrons flow freely, and insulators where they barely move, semiconductors can be tuned to conduct electricity under certain conditions. By adding tiny amounts of certain impurities in a process called doping, we can make the material more conductive or even determine the type of charge carriers it will have, if it's positive or if it's negative. This ability to control conductivity makes semiconductors perfect for making electronic components like transistors or diodes, integrated circuits. In these devices, we can manipulate the flow of charge to process, amplify, or store information, making semiconductors the backbone of modern electronics. One of the interesting things about semiconductors is that we can have both positive and negative charge carriers. Depending on the type of doping, adding impurities to alter its properties, semiconductors can either have holes where electrons are missing and behave like positive charges, or electrons as the main charge carriers. By using the Hall effect, we can figure out which type of charge carrier is dominant in a semiconductor. If the Hall voltage suggests that the dominant carriers are positive, we know we are dealing with a p-type semiconductor, p from positive. If they are negative, it's an n-type semiconductor, n for negative. This is essential in semiconductor manufacturing and research, where knowing the carrier type is crucial for designing devices like transistors and diodes. So next time you use anything with a magnetic sensor or think about the way charges move in fields, remember the Hall effect and how it helps us measure, sense, and understand the properties of materials at a fundamental levels. Let me know any questions in the comments below, and may science be with you.